All right, so for exception handling, we said we can have two different types of events that can cause an exception. One is the hardware, so like a discrete error, end of file, and so forth. And those are, that are some of these actually are software detectable, like if you have it in your language that can detect subscript range errors or something like that. So the exception in this case is an unusual event, and it can be detectable either by a hardware or software. And we have a few parts of the terminology. One is exception handling. It will actually, the special processing or a part of your, let's say, logic that handles or that is required to be executed once you detect actually your exception, once the unusual event happens. This processing is done by a code unit or some sort of a segment called exception handler. The handling process is actually doing that, and the code to do this is a handler, exception handler. An exception is actually raised or thrown in some cases when the associated event, unexpected event happens. So there are, once we decide that we don't want to resume the exception, perhaps, or we want to resume the exception instead of terminate the program, the user there is a possibility to actually add both user-defined exception handling and perhaps also user-defined exception, let's say, throw or exception raising possibilities or capabilities. Okay, this is, you can do this again, these techniques to actually use it to handle software detections and doing the software detections by yourself, or for this let's say, unusual events. And for this one, you have several different things. One is status variable flag, which is actually keeping track, or which is assigned a value in a subprogram according to correctness of your computation. And then there is a label parameter in the subprogram to make the return different locations in the caller according to your value of that label. These are used in things like C libraries and C and Fortran, because they don't have a built-in exception mechanism. When you have a built-in exception mechanism, you can actually these offer some advantages. The code required to detect the error conditions can be actually quite simple in this case, versus if you want to do this by user, right? So we do these type of things very often when there is no, let's say, exception handling mechanism for, let's say, end of file. So in C, we usually have a program or some sort of a statement that detects that end of file thing, or let's say file doesn't exist thing. And then we define some logic to actually handle this. So the code to do this one could be quite cluttered. When you have a built-in exception handling, this would be easier, of course. And another advantage of this one is exception propagation. So you might actually have, if you have an exception raised in one block of your code or one unit of your code, it can be either statically or dynamically propagated to another block that is not actually part of that unit, or another unit of code that can actually still track that exception or can handle that exception. And if you have a built-in exception, another advantage is that you can force your programmer to think about what would happen. So if I know that, for example, I mean, you see this in Java and C, like C++ like type languages, where if let's say if a statement or an expression can encounter or is likely to encounter an unexpected event, then the language will actually force you to somehow, let's say, react to it, meaning you have to have some sort of resumption policy. Of course, this doesn't mean that you would respond to it. You can still ignore it, and in many cases we do that ignoring. So we say, okay, we write a catch statement, but we don't do anything in that catch statement, perhaps, or we just terminate. But at least what's happening is that the language itself is forcing you to think about it. Even if it is just a termination, you are aware that there is something happening there. Otherwise, you might not be aware of that fact. So this is another advantage. And this is the kind of probably, I mean, this is the main advantage, one of the main advantages in to enforce some sort of reliability. Of course, these are, again, tools, but they can be always, let's say, bypassed by the programmer. All right. So you see an example here. We have an assignment and expression, and this expression is expected to actually do cause an unusual event when the total is actually less than 0 or equal to 0. And your compiler may say, okay, wherever you use let's say a division operator in an expression, the compiler say, okay, I'm going to force you to actually take an action because I know that division operator is actually going to cause an exception in some cases, and I will have a code, a handler to take care of what is happening there, right? So in this case, this guy is actually resuming. Of course, there are a lot of decisions that we have to do here. The question is, we are resuming, but where are we resuming from, right? So this is not defined here, but at least this is saying that when there is an error here, or there is an unexpected event, I will actually handle the result as average as 0, and then I will print something and I will continue. The question is, where do I continue? Do I continue right after this, or do I resume it from somewhere else? Do I do this? Do I do that? So these are going to be other decisions that we have to make, and we are going to discuss. The first thing is actually exception binding in the design issues. The question is, I know that exception happened, and I need to tie that to an exception handler. Where is that exception handler that will handle this thing? This is not a trivial thing. This is a quite complex. It can be quite complex. So one thing that you can force is you can say, okay, I want to do this at a unit level, meaning wherever the exception happens, like this case, for example, this says, I'm doing this unit level. I'm expecting the programmer to actually write a handler at that unit where the exception is likely to happen, right? So there is a division operator, and I'm asking that division operator to be at least the portion of that thing to be handled within the unit itself here. Perhaps there are other parts of the thing that needs to be done here. Maybe there are other exceptions, and I can actually force them to be within the unit. All right. Of course, there is a potential disadvantage of this one, because if I need to actually handle everything but at the unit, what will happen is that I have, let's say, at this unit, I have a division, and another unit, perhaps another function, has a division as well. Now, I need to write also in that case a handler for that. So this can clutter. This can force me to write a lot of handlers. Perhaps all of them are serving the same purpose, right? So this might be a little bit difficult in terms of writing them. So another question is I can actually handle this at higher levels. If there is no exception handled at the local level, can I actually propagate to a higher level? So I have a function, and within that unit, I have a possibility of exception. I'm not going to handle it within this unit, but I may handle it within another nested unit, perhaps, or another nested unit, and so forth. So the question is, can you allow that? Yes, you can do that, but then you have to be this type of, let's say, higher level. You have to decide where, up to which point I can allow that. And in that case, tracking of these things will become a little bit difficult. Of course, you have to decide what you want to do here as part of the decisions that you have to take as part of design issues of your programming language, right? Another thing is that continuation. How do I continue? So after the execution handler executes, either control can transfer to somewhere in the program outside of the handler code, or program can actually terminate. The execution can terminate. Now, the decision of actually where to go, and if you have these type of higher level or unit level decisions in terms of where you do the binding, will actually define how you can go back. So if it is at let's say at a higher level, you need to know how to go back to a location where the execution can resume. Okay, so we discussed this. Termination is a simple solution. You just terminate. Another one is actually it might be useful when the condition encountered is unusual but not erroneous, meaning I can correct this. At least I can take a corrective action. So then the question is, where do I return? Do I return at the statement that raised the exception, at the statement following the statement raising the exception, or at some other unit? So these are all decisions that you can actually make. So you can say, okay, I will go to the next statement, or maybe I will repeat that statement itself. We usually see that actually things are done usually going to the next statement, perhaps, or maybe there is no return at all. So the exception handler actually terminates it. So these are the decisions that you have to have. There is another one that is called finalization. So maybe this is what you want to do. Your exception handling mechanism says, okay, you do it, you terminate, but before you terminate, you actually have a final action that you want to take. And always you take those type of final actions. So to complete the computations at the end of the execution, regardless of whether the program terminated normally or because of an exception, you might be actually doing always this finalization action, right? So this is, for example, Java has this one. We are going to discuss this in a few minutes. And then the other question is, how are user-defined exceptions specified? Do you allow a user to, let's say, raise an exception? How does that happen? Are there predefined exceptions? Compiler or language defines some predefined exceptions, like, let's say, division by 0. Should it be possible to disable predefined exceptions? This is also very critical. You know that, for example, your programming, what you do, let's say, will never actually do a 0 division by 0. So would it make sense to actually disable this? What do you think? Would you disable a predefined exception in your language? Would you allow it? Would you allow it? You don't know. It may be good. How?
Some problems before they execute.
Okay. So why do I actually, let's say, disable a predefined exception? Why would I disable a predefined exception? I have some predefined exceptions in my language. And I always want, let's say, division by 0. And I always want you to actually take an action. When you use a division, I say, okay, you have to have a handler to actually define your actions once that happens. That's the thing that I want to do, right? So why would I actually disable that? So I'm talking about the mechanism. I'm saying, okay, yes, I have a division by zero exception, and I normally ask you to actually write a handler for it, but you can also disable it so that you don't need to write a handler. Flexibility, of course, right? So you don't want to deal with always let's say the exception, but there is the first decision that you made. You said, okay, it is important for me to have these exceptions handled. That's why I defined as a predefined one, and this means that a lot of people need to actually think about it. So these are, I mean, flexibility is good. Maybe I don't need to worry about it. But when I actually put it there, I say, okay, hey, this is important, and at the same time, okay, don't worry about it. If you want to, you can actually disregard it. It doesn't make too much sense to me, actually, at least. Okay, another question. If you have a predefined exception, would you want to have a predefined handler as well? Why not, right? So I know that there is a division by zero, and I will say, okay, there is a predefined handler for that. It actually says, okay, there is a division by zero happening, and I'm bailing out. But again, if this is the case, then why do I have it? Maybe this is a little bit better than disabling it, but still, then you are not asking the user to or the programmer to actually think about things, right? Think about what might be the consequences of those unusual events. All right. Explicitly raising those predefined exceptions. This is another question, right? How about hardware detectable errors? Are they treated as exceptions that may be handled, or do you actually, again, predefine them and so forth? These are all questions that you have to have. So exception handling is tied heavily to types, right? So in the case of Java actually has this throwable thing, and it has two types of throwable things. One is error, the other one is exception. And for exception, it has runtime exceptions and IO exceptions. And for runtime exceptions, you have like things like out of bound exceptions, null pointer exceptions, and so forth. Some of these are actually predefined and run out of memory, for example, heap memory exceptions for errors. And these are, some of them actually are generated by the JVM. And the exception handling mechanism is something like this. When you have a code that is expected to generate or raise an exception, you put that code inside a try block, and then right after that you have a catch block. All right. Now you can see that this catch mechanism here, or the handling mechanism here, the binding is actually happening at unit level. You can see that this is happening at the unit level, at least in this particular case. So in this case, an exception is thrown using the throw statement. You can actually have a throw statement to throw something like this. You know this one from your Java classes. So you have an exception and then a message indicating the state of the exception. The binding happens if an exception is thrown in the compound statement of a try construct. It is bound to the first handler, or the catch function, immediately following the try clause, whose parameter is the same as the class as the thrown object. So whatever the thrown object is here, this one, as long as there is a catch function following the try block, it will actually catch it, or an ancestor of it. So it doesn't need to be just itself the same class, but it can be also an ancestor class. If a matching handler is found, the throw is bound to it and it is executed. And the finally clause, there is Java supports this one. And in the case, a process actually has to be executed regardless of whether an exception is raised or not and handled or not. So this is finalization, meaning you actually, if you either go through an exception or handling, or you actually go through a usual path, and then at the end of the usual path, you have this final clause that you actually will will do no matter what. So these things can be used to, let's say, take care of things like, let's say, handling a file handler, open file handler, or some resources that you actually needs to be released as part of the finally class or finally statement or finally class. Right? Okay. Events are a little bit similar to these, but they are concept-wise they are different. Handling mechanisms could be similar. An event is actually created explicitly by, exceptions can be either created by explicitly by user or implicitly by the hardware or software interpreter, right? On the other hand, events are actually created by external actions, like, let's say, a keyboard hit or, let's say, a GUI interactions and so forth. So this is used quite heavily in event-driven programming, and parts of the program are executed at completely unpredictable times, triggered by the user interactions with the executing program. So you have an event handler similar to exception and exception handler, and you can see similar concepts here. So again, going back to the definition of the things, we are kind of using similar concepts in different ways, in different places, so that the understanding of that concept could be actually easier. So you could have used a completely different event handling mechanism, but once you know exceptions and you can now easily understand event handling, or once you know the event handling, you can also easily understand exception handling. I'll skip these. There are some issues regarding static scoping of declarations for handling exceptions within ML. These are concepts that we have discussed. One thing that could be important is the typing of an exception. How do we type an exception? So you need to, the first thing that you need to do is actually you have a type of a raise, or let's say throw, exception throw mechanism. So in this case, expression E has a type T if normal termination of E produces value of type T. So let's say that you have an expression, and you know that if this normally happens, this will generate a type T output, right? So typing wise. As I said, we didn't discuss typing before when we were actually thinking about applicative order or let's say normal order evaluation. Now we'll discuss this a little bit. So the question is, of course, typing is important. We need to actually understand how we are going to use it later and so forth. But what happens if there is an exception here? What will happen to this type, right? So if I actually use this type in the normal case, in the usual case, what is going to happen in an unusual case? Raising an exception is not normal termination, right? So there has to be so one way would be that, okay, this will actually give me type and something else, right? So this could either return a type or return an exception. In this case, the typing of this thing, what is it? Is it defined, or we have to actually make a decision here? So in case of, let's say, these languages that actually stick it, or let's say using a very strong typing system, they actually think about this a lot. So what happens is that when you have an exception, so when you have an exception and when you have a handle to it, one mechanism could be you return a value out of this exception. Perhaps this value is going to be, let's say, defining again your resumption mechanism, but the value type of this thing and this guy would be the same, needs to be the same. So in this case, I can say, okay, I can use this expression no matter what, in usual case as well as unusual case. For example, your thing could be, the handler could be something like this. If I have an expression and there is a division by 0, my handler can say, okay, I'm going to return the same type, but 0, or but 1, but maybe an infinite number, or whatever, right? but I will return as part of my resumption a value that this expression can take. But the question here is that, or the important thing here is that the type of this value that I return and type of this expression here, or this type, has to be the same. They have to agree. All right. So if you want to design something like this in a functional language, you have to actually take into account. Now, but of course, this is not an easy thing to do again, because let's say, the exception in that particular expression may have happened because of, let's say, some hardware error, like maybe, let's say, a memory allocation. And in those cases, you need a solution as well for these type of things. And these are general problems, but there are now obvious solutions. And discuss a little bit about what may happen with the memory. And in this context, we are going to discuss a little bit garbage collection. Garbage collection is usually not seen as a, let's say, language feature, but it is an important thing to know anyway, so we discussed it here. We discussed, if you recall, major areas of memory as static area. These are fixed size, fixed content, allocated at compile time type of places. Runtime stack, variable size, variable content in terms of activation records, and they are used for managing function calls and returns. And then we discussed about heap. Heap is actually a fixed size, variable content and memory, and dynamically allocated objects and data structures actually are in heap. Let's say malloc in C, new in Java, and so forth. These will be part of heap. Now, since these are actually management of these are quite easy, right? So we know this is managed at runtime. This is managed as a stack. I know how stack works, so there's no problem here. As long as I have enough memory for stack, I can actually do this implementation. But this is a little bit difficult, right? So I will need to have a manager, some sort of a memory manager that takes care of this heap for me, right? So this is an unstructured memory. And what we do is we define a few things. We define a cell as a data item in the heap. So cells are usually pointed by pointers held in registers or stack or some sort of static global or static memory. And perhaps also they may be actually pointed by other memory cells in heap. So this is kind of where the difficulty starts. If this was all handled by registers, stacks, and some global memory or static memory, having this will actually make it a little bit difficult. And we call a root or roots as pointers that is held in register, stack, or global static variable, not in other heap cells. And there is a simple definition of a cell being live. If it's actually a cell is live or can be live, as long as its address is held in a root, as we define, or held by another live cell in the heap. Meaning the compiler or the program at runtime or wherever can access this cell. There is only two ways to do this one. Either the pointer, there is a pointer which is kept somewhere in the registers or in stack or in global or static variables. These are the roots. Or it is actually called in a cell in heap, which is also live. If it is kept in a cell in a heap, but it is not live, this means that I cannot actually access that memory at all. So this is important. Now, in this case, we can define the garbage as a simple thing. It's a block of heap memory that cannot be accessed by the program, meaning cells that are not live or cells that are dead by the definition that we actually discussed. An allocated block of heap memory does not have a reference to it, meaning it's not live, it's no longer live. And another kind of memory error could be also a reference exists to a block of memory that is no longer allocated. All right. So garbage collection is an automated management of dynamic allocated storage, especially reclaiming this unused heap or dead heap, dead cells by the user program. Right. So there is a simple example. You must know this one from your programming courses earlier. So I have a class which has two fields, value and node, next and integer value and node next. And I define two instances of this. I generate two instances of this class, P and Q. I take P as a new instance of node. I take Q as new instance of another node. And then I assign Q to P to Q, meaning now P and Q refers to the same node as P, and I delete P. In this case, when I delete P, I know that Q is already the original Q, the second Q that I actually, or second node that I allocated here, which is in this case here. This is actually now remaining in the memory. This is not live because there is nothing that can access that particular cell. There is no reference to it. The reference is lost. All right. So the garbage collection should actually handle those things. One of the things that we do is, I mean, today's programming is not as efficient as, let's say, 30 years ago or 40 years ago, because we have a lot of memories. I mean, when I wrote this one, like, I don't know, in 2012, 13, 16 gigabyte was a lot. Now we are talking about, let's say, laptops with easily 180, 28 gigabytes memory. And with virtual memory, with a SSD disk, this can be on the order of terabytes, right? So a lot of memory these days we are talking about. So we use these storage freely, but still we mismanage it. Memory leaks, dangling references, double frees, misaligned addresses, null pointer dereferencing, heap fragmentation, and all these things still happen. So there is also poor use of reference locality. So if you have, let's say, an array or let's say several variables that are used quite often, if you don't have these in, let's say, in locally in similar blocks or close enough blocks, your hardware will actually do a lot of caching. So you are going to learn about this. Probably you learned a little bit about this in your architecture courses, and you'll learn a little bit more about this in your operating system course as well. So in this case, you need to actually do this memory management and help with these high-level abstraction processes. Now, of course, this is when we talk about actually handling this, we are talking about a secondary program or secondary algorithm to actually manage this for you, right? So when we talk about a secondary thing, that means that it's going to steal cycles from your, let's say, CPU or from your, let's say, memory and so forth. So this has to be quite efficient. All right. A perfect garbage collection should not be visible to, in terms of impact, should not be visible to a program execution. So a program execution should be actually not impacted by at all by your garbage collection. If you have it or if you don't have it, it should be seamless, meaning it should not actually cost you anything. But this is not going to be the case. It will cost always something. So this is the perfect case. In the perfect, again, the perfect garbage collector should have should work with any program and its any data structure. All right. It should collect garbages quickly, and it should have excellent spatial locality of reference. So things should be actually clustered together. Meaning, if I have 5 variables that I'm using in this part of the code, those 5 variables should be on the same part of, or spatially, they should be within the same area in the heap so that trashing doesn't happen. And then it should also manage, in general, heap efficiently. Fragmentation and so forth should not happen. So if I have, let's say, a bad manager, I may have, let's say, an integer that I actually, let's say, require from time to time dynamically allocated, a small space here, small space there, small space there. And then all of a sudden I need a big space for something, and there is nothing that I can fit that big space into my heap because I have a fragmented heap. So the fragmentation should not be there. So there are several things that several algorithms that tries to actually get this perfect garbage collector. They never get the perfect, but they can get close. One easy technique is actually reference counting, and the other technique is actually tracing. Let's look at the reference counting. Reference counting is actually, what you do is you simply count the number of references to a cell. Okay, so what you do is when you have a cell in your heap, all right, so this is your cell in your heap, what you do is you actually have a counter, reference counter, saying that how many people are actually referencing to this guy. Okay, here you see that this guy is actually referenced twice because one is here and one is here. This guy is referenced only one by a root. This guy is actually referenced twice by another cell here, live cell, and hopefully another live cell here. All right, so this is just a simple thing. Of course, as I said, efficiency requires I cannot actually put a lot of overhead memory next to actually what I want to do. So these are the things that I want to do. These are the, let's say, my linked list here, and this is the additional thing that I want to put, my memory manager puts on top of the linked list that I need from my system. All right. So you simply count them. You require some space. And what happens is that when you add a reference to your, let's say, to this thing, you increment it by 1. So if I have another, let's say, if this guy somehow breaks this one and goes here, so this will go to 2 and this will go to 0. All right. When I dereference something and I reference something, I will actually update this value and then let's say remove that value. And then once I actually have this type of a thing, what I do is when I'm done, let's say from time to time, I will actually go and say, okay, now I need to collect some garbages. I can have some metric to do that. I say, okay, I need to collect garbages. Everything with a 0 reference will be garbage for me. I will return them to my heap. Right. So this is a simple one. So there is a space overhead. This is one problem. And this can also actually cause dangling cyclic structures with cycles will actually may cause leaks here. There is an example. So you see actually when you have this one removed, right? And you remove this one, this goes to 1 from 2. Now this guy is live because there is a reference here, and this guy is alive because there is a reference here, but this cannot be actually accessed by outside. Now you can perhaps catch these cycles, but then what you need to do is you need to actually go after them. And going after them is going to be much more expensive than just counting these numbers and actually reclaiming what you have as zeros. Niye herkes hazırlanıyor da 10 dakikamız var? Böyle. Çıktı mı? Okay. All right. So another possibility is actually, so some, let's say, these type of, let's say, garbage collection mechanisms are actually implemented in some of the libraries like smart pointers in C++, sorry. And another algorithm is actually mark and sweep garbage collection. So what this does is actually it has a mark bit, and garbage remains unreachable and undetected until heap is used up. And then in marking phase, what it does is actually takes this, and then it will start from the root and actually mark everything that is touched. So it will touch this one, 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 it will touch this one. Now, these are not going to be able to touch from your thing. and then it will be actually removed. Things with a no mark will be removed. But you see that this mark sweep algorithm is going to be expensive because you need to actually go through the entire thing, right? So it's very difficult. And then there is another one which is more expensive, but perhaps useful, copying collector. What it does is actually it takes your thing and it actually copies to space and then back to another space. And during this copying, it will actually get rid of the unreachable ones, the non-live ones. And the advantage of this one is also it can actually enforce some sort of defragmentation of your memory. So it will actually be most useful for defragmentation, whereas these are nothing, these are doing nothing as far as defragmentation of fragmentation of your memory is actually concerned. All right. Let me see. And there are some, let's say, modifications to this copying stuff with aging and so forth, but I'm not going to get into details of those. Okay, I guess this is sufficient for garbage collection. Now what we'll do is next we'll talk about, let me see, what are we going to talk about? We're going to talk about procedures, and the main idea of procedure and functions, the main idea being the how do we pass arguments to functions and procedures, and how we return arguments from functions and procedures. We are going to explore those next time. And then after that, we'll be talking about some abstract data types. And then after abstract data types, we'll be talking about object-oriented programming, functional programming, and logic programming. And hopefully we'll be done. All right, any questions? So the exam will be, midterm exam will be on the 19th at hopefully at 5:30 p.m. late in the afternoon or towards the evening hours. It will be for 2 hours, and it will be in this building somewhere here. And we'll be issuing or sending a questionnaire to collect the attendance. Maybe some of you already dropped the course. Some of you may not attend the exam because it is face-to-face, so or in person. Okay. Other than that, I'll see you. As I said, I may not have a lecture on Wednesday. I'll let you know on tomorrow evening. If that is the case, I'll see you on Monday, continuing with the procedures.
So 19th,
19th is next Friday, not this Friday, but the Friday after. Bir dakika, hiçbir şey duyamıyorum.